Thank you for joining in today's webinar. So today we are going to look at into pump performance monitoring through model-based electrical signature analysis, and we will explore the pump performance monitoring through electrical signature analysis, how it is performed, and how we utilize factors such as head, flow rate, and efficiency in order to keep track of pump's performance, and also how we merge this information together with the existing electrical, mechanical, and process fault detection capabilities of model-based electrical signature analysis, and then identify potential issues such as wear and tear and cavitation or inefficiencies through comprehensive analysis of pump curve data, again, with combination of electrical mechanical faults. So for those of you who are already aware of the capabilities of model-based electrical signature analysis, that you know that through voltage and current, one can monitor the rotating asset, whether it's a pump or fan or conveyor compressor. And with that, you can see the electrical issues, whether it's on the power circuit or incoming power, or through the mechanical components of the rotating asset. This includes the electric motor itself, the drivetrain, and the driven equipment. Now, on this particular webinar, we are going to focus on a new feature that we are launching, which is going to be monitoring the pump performance curve, again, through estimating its flow and head and efficiency. So, and one second. Okay, so, and the information that will be provided, you can see here briefly, will be of course, the operating points of the pump itself, the trend of the flow, power consumption, and more importantly, of course, the actionable information will be provided to the user, whether the pump is operating at its best efficiency point, if it's not, if it's going on this curve towards left, which would suggest issues such as temperature, noisy operation, high vibration risk, cavitation, bearing or sealant damage, or whether it's running at actually inefficiently. So, with that, how much the total energy consumption, how much energy consumption or savings can be made, and what is the associated savings in terms of dollar or euro or whatever the currency you're using. So, but of course, before getting into all of that, we are going to start with understanding how a centrifugal pump work, and then we will look into the key performance parameters of the pump, and then how we look into different pump curves and what individual curves would mean, and then how we combine that with electrical signature analysis. So, starting off with the pump operation. Sorry. Okay, just bear with me for 1 second. I'm having a hard time here. Okay. Apparently this is not working. Okay, so the centrifugal pump, of course, consists of a power input, which is the electric motor, or in some cases it would be a generator or even diesel engine, which provides the power through the shaft to the impeller of the pump. And with that, the pump, of course, the impeller starts rotating, and then you create suction power, and that sucks the fluid that it needs to be transferred from one location to another, and through the casing, you discharge the fluid through the outlet. So, and it's a very simple mechanism here. So, of course, there are factors that affects the flow and the ability or the capabilities of the pump. We will look into those individually later on. So, the first and the biggest component of any centrifugal pump would be the impeller. So here, through, of course, the impeller, you create the rotation, and then with that, you create actually a kinetic energy, which will start rotating the fluid here. And through the eye of the impeller here, you will create a negative pressure, and which will create the suction power of the fluids, and then the rotation will, through the casing of the pump, discharge the fluid. So this is how you create the inlet suction power, and then you transfer that through the outlet and discharge it to another location, which is usually the high pressure zone. All right, so in the impeller, there are several key components that we should keep an eye on to keep track of the mechanical performance of the pump itself. And this can also be seen through the electrical signature analysis. If you have problems with your impeller or bearings or bearing housing or the seals, this can actually be seen through the spectrum analysis. But having the ability to monitor pump performance before it affects the mechanical components of the motor, you can actually prevent these damages earlier. So now, in order to understand how we keep track of pump performance, we need to understand what parameters that we will look at. There are three main or key pump performance parameters. The first one, the flow rate. So this flow rate, of course, would indicate the volume of fluid the pump can move within a given period, which is crucial for determining pump capacity and application suitability. So the second one is the head. So head represents the pressure or the energy provided by the pump to overcome the resistance or the gravity and to lift the fluid to the desired height and determining maximum pumping height. So basically, head would mean how much further you can pump the fluid, or what is the capacity of the pump. And the efficiency reflects how effectively the pump converts the input energy into useful work. This is also crucial for minimizing energy waste and operation costs. So starting with the flow rate. The flow rate, also known as volumetric flow rate, is the volume of the fluid passing through a given cross-sectional area per unit of time. This is usually measured in liters per second, cubic meters per hour, or gallons per minute, depending on where you are geographically in the world, and typically measured by using flow meters. So, and the importance of a flow rate, of course, this is typically used in industries in different applications in order to determine the size of the impeller or the pump capacity. So, and without that, you don't have the ability to size your pump or again impeller. So it is calculated by dividing the cross-sectional area, by multiplying the cross-sectional area with the velocity of the fluid. So there are some factors that affects the flow rate. This is going to be very important, of course. The pump speed, the impeller size and the impeller type, viscosity and density of the fluid, the system head, and the pressure losses. So, and we will look at these individual factors later on, but for us, the most important one would be the head as well as the speed, because these are, or the pressure, these are the variable parameters in most systems. The impeller size or impeller type, it would be harder to change. And these, we are going to monitor the speed and of course the head and pressure of the system. So these are the ones that we will pay more attention to. The second parameter was head. So again, a head refers to the height to which a pump can raise the fluid against gravity or the pressure energy imparted by the pump to the fluid. So this indicates the maximum height the pump can overcome, again, to move the fluid through a system. This is very critical for applications requiring lifting the fluid to elevated locations or overcoming the resistance in pipelines. So, and there are two components of the head. One would be the static head, which is the vertical distance from the pump's inlet to the highest point of discharge, as you can see here. Over there. The second one is the dynamic head. This is the resistance encountered by the fluid during flow, including friction losses and elevation changes. So, and determining pump suitability for specific tasks such as water and supply system, or at different applications, you have to know the head, how much, how high you would want to pump the fluid. So, and this is, of course, needed for assessing the system requirements and pump performance optimization. So one thing you have to consider is, in order to ensure the pump's head rating, that it meets, the pump selected for the job meets or exceeds the head requirements of the application. And also you have to take into account the friction losses, elevation changes, or system pressure when calculating the total head. And the total head is, or the head is typically measured in meters or feet. So, but we also sometimes refer to head as pressure in the system. So pressure is measured in PSI. However, the head is shown in meters and feet. This is because the head is fixed here, but the PSI, the pressure, would depend on the fluid type that you will actually pump. So, and that can change. The third one, or the third key parameters that we are, of course, going to look at would be efficiency here. So the efficiency refers to the ratio of output power to the input power in a pump, indicating how effectively the pump converts the energy into useful work. So, and of course, the input power to the pump would be the motor's output power. So you have an electric motor, in this case, that powers the pump, and how much of that energy or power will be converted to an effective use of the incoming power. So this reflects the pump's ability to minimize energy waste and operation cost. And of course, higher efficiency would lead to a reduced energy consumption and environmental impact. So, and this is typically measured in terms of percentage, and you would have the efficiency charts of the pump provided by the manufacturer, which we are going to look at shortly. So there are several factors that affect pump's efficiency: the pump design, operation conditions, fluid properties, and the maintenance. And this is, of course, where our interest lies here, because at the end of the day, through the pump performance monitoring, we would like to know and show to user whether this pump is running at its peak efficiency. If it's not, then you would be aware of that fact, and then you can take the necessary actions to get the pump at efficiency or optimize its performance for a given flow and head requirement. Now, we have taken a look at the key parameters of flow, head, and efficiency. And of course, efficiency had to do the usage of power. So, and there is a relationship between these parameters and the speed of the pump, assuming that the impeller size remains constant. So, and the affinity law basically are a set of mathematical relationships here, which provides an insight how changes in operation conditions, such as speed adjustments or impeller size variations, affect the performance, energy consumption of the pumps. So this is essential, again, for engineers or for users to design and understand to optimize system performance and efficiency. So we'll start off with some simple example. So if you reduce the impeller speed by 20%, the flow will reduce by 20%. So there's a direct relationship or proportionality between the speed and the flow rate. However, if you look at the head, it will actually reduce by 36%, and the power will be reduced by 49%. Now, let's look at individually each of these parameters so we understand them better. So the flow affinity law, this describes the relationship between the flow rate of a pump and its speed. So, and of course, it will help us predict how changes in speed affects the flow rate. As you can see here with this formula, here, of course, Q1 and Q2 being the flow rate 1 and flow rate 2, and N1 being the speed 1 and speed 2. So there's a direct proportionality between the two. So this means when the speed of a pump increased or decreased, the flow rate will change accordingly. So an example, if we double it by 2, and the flow rate will double too. So in this example, you can see that we are increasing the speed from 1200 RPM to 1500 RPM. So the speed will increase 25%, and the flow will also increase 25%, which will go from 500 liters per minute to 625 liters per minute. So it's a very simple concept to understand, as the relationship between are directly proportional. One thing we have to keep in mind here is that we are keeping the impeller size constant, because that is also another factor that affects the flow rate. So and of course, it is really not practical in everyday applications where you can control the speed with the VFDs to change the speed. But however, changing the impeller would require a more significant time and effort to do that. So this law, again, assumes that the impeller size remains the same, and changing the speed will affect the flow with the same proportionality. The second law here we are going to look at is the head affinity law. So this important principle, again, describes the relationship between the head and pressure, between the head and pressure by a pump and its speed. So, and the relationship here between the speed and head is squared. So, which means that when the speed of the pump is increased or decreased, the speed will change with a factor of squared. So, and in this example, you can see that we are increasing the speed by 25%. So this 25% increase on speed will yield to a 56% increase on head. So it will go from 50 meters to 78 meters. The third law is the power affinity law. So this law describes the relationship between the power consumed by a pump and its speed. So you can see that here we are increasing the speed again from 1200 RPM to 1500 RPM. This is an increase in 25%, but the power requirement to achieve the same amount of 25% speed increase will cause the pump to consume 95% more power. So, and there is a cubic relationship here. So, and this also, of course, represents the significance of efficiency, because any increase in the flow, any requirement to increase the flow will cause you an exponential power consumption. So this also indicates the need for an efficient operation of the pump, so that you can save energy, and then you don't waste a lot of energy for being able to do the same job. So in this example, we are going to combine all these affinity laws into one single example so that the laws and the relationship between them are clear. So you can see here we have a pump curve. On the x-axis we have the flow, the y-axis we have the head. So we are going to look at what the pump performance curve would look like later on, but bear with me for a minute here. So we are starting with 100% speed. This is a 4-pole motor, so 1475, and that's at this speed the flow rate is 342 cubic meter per hour. Our head would be approximately 14 meter, and the power consumption at that operation point would be 17 kilowatt. Okay, so let's assume that we want to reduce the speeds to 1121 RPM. This is a 24% decrease in speed. So that will move the flow rate from 342 to 259. So of course we know that through the flow affinity law, because we reduce the speed by 24%, which is reducing the flow by 24% from 342 to 259. And there we also know how to calculate the head, because that was a proportion to the square of the speed. So which will then reduce the head from 14 to 8. So you can see that this is our operation point, and the power was again it had a cubic proportion relationship. So the power requirement went down from 17 to 7. So this is approximately a 60% decrease in power requirement. So you can see that how changing the speeds will affect the flow, head, as well as power requirements in a pump system. So now we have used the example, and in that we had the pump performance curve. So we are going to look at the pump performance curve of flow and head curve, and efficiency and the system curve, so that this will all make sense for you to understand. And in combination of all these curves, we can actually have some actionable outputs from the pump, and we know what it's doing, and if it's running efficiently, or if it's actually cavitating, or if it's actually close to a shut-off head point, so where the pump gets, the temperature of the pump gets higher and higher, so which will of course risk damaging the pump bearings and seals as well as cavitation. So looking at the head curve, or the QH curve, the flow and head curve here. So this is also known as pump performance curve. This is depicting the relationship between the flow rate and head. So, and developed by a pump under varying conditions or varying operation conditions. So the x-axis, of course, represent the flow, and the y-axis represent the head. So, and this curve represents, pump's head varies with the changes in flow rate. So you can see here, it also has the speed. So there's not one single pump curve, right? So at 100%, this is your pump curve. At 90% speed, this is your second pump curve. So there you can have as many curves here dependent of the speed. So this is important, and the curves of the pumps are provided by the manufacturer. When they manufacture and design the pump, they test it and they provide the data sheet for it. So of course this is later on used in selection the proper size of the pump and for a particular operation, and even also help optimizing the system performance by adjusting the pump speed or impeller size to achieve desired flow rates and heads efficiently. So the second curve is the efficiency curve. So the efficiency curve represents the efficiency of a pump across a range of flow rates or operation conditions. So this illustrates how pump converts the input energy into useful work at different flow rates. So if you look at here, so on this curve, we have the flow rate, and the y-axis on the efficiency chart is the efficiency points over here. So you can see at different speeds and different flow rates, we have different efficiency curves. So for instance, in this example, across from 380 to all the way down here, the efficiency remains constant. So, and of course, by following this curve, we can keep track of the operation point of the pump and see if it's running efficiently or not. So the efficiency curve will tell us that. So of course, this will be used to, again, optimize the pump's efficiency. In return, of course, reduce any energy waste and maximize the optimum savings here. And there is also a term that we are going to use in our software and chart, so the best efficiency point, so that the users will be able to keep track of how much it deviates from this best efficiency point. So in this example, you are looking at one chart, which is showing the best efficiency point only for one speed. Again, if you go back to here, you can see that the best efficiency point will move between these curves dependent on the speed. So this is important to understand. So in this example, now if you can keep track of these values over here. So we are running at, the flow rate is 342. So at this level, the efficiency of the pump is, you can see here, is almost 77%. So if we were to change the flow rate without changing the speed, you will see that this operation point will move towards left or right. And if I move to the right, which means that the efficiency of the pump will actually decrease towards 60%. And if we throttle the pump to the left, so without changing the speed, you can see that this is going to move over here, so the efficiency will decrease. So, and having the efficiency curve will, of course, help us determine, again, the performance and efficiency of the pump. So, and through the P2 curve, of course, which is the corresponding point to these points, will help us, again, to keep track of the power consumption. And final curve that we are going to look at is the system curve. The system curve is essentially the multiple curves for different speeds. So you can create as many curves, again, with small intervals between speed changes. So this will give you a best efficiency point across variety of operation points and speed requirements for the system curve. So this is essentially an imaginary curve created and calculated by the software. So every time you change your speed and flow and head, it will calculate a new best efficiency point, and then it will keep track of that point with the actual measurement. So this is going to be the reference point for that. So if you, let's say you are at 90%, and so your flow reduced by 10% from 340 to 310, and you're calculating this is your best efficiency point. However, if the actual measurement shows that the pump is over here, which would then suggest, yes, this is not at its maximum peak efficiency, rather it's deviated from that. So of course, this is the information we are after here, and system curve will be the reference point for that. So now let's look at some of the flow rate control methods, right? So because at the end, the goal here with the pump is to pump some sort of fluid from a low pressure point to high pressure, and the parameters that we were looking at was flow and head and efficiency. So the parameters that we can control is the flow here, right? So, and there's two ways to achieve a flow rate control. One is the throttling, and the other one is speed control. Okay, so throttling is done with a valve. So in this example, we will look at what happens when we do the throttling. Okay, so we start off with, again, 342 cubic meters per hour. The head is 14 meters at that point, and the power consumption is, or the efficiency is actually here. We don't have the power. It's around 67%. Okay, so this is very efficient, almost is at peak efficiency. So now when we throttle the pump again, we cut the control, the flow rate from 342 to down to 200. So this is approximately a 42% decrease in the flow rate. And so that translates into a head of 18. So if you can see here, we didn't change the speed, but the pump, of course, will move at this curve. So the speed is the same, and therefore the head increased, and which will then reduce the efficiency of the pump. So this is similar to, let's imagine a car where you're pressing the gas pedal at full throttle, at the same time you're braking, right? So this is inevitably will cause some inefficiency. So that's also manifested here in a pump application. So while you're keeping the speed at the same constant rate, you're throttling the pump, which will of course create inefficiencies, and that inefficiency will show itself as heat. So the second method to do then the flow rate would be to use a VFD, and with that you can see how efficiently the pump will run. And so pay attention to here. So the efficiency when we were doing the throttling went from 77% down to 6. So there's a 10% efficiency decrease. So when we achieve the same flow rate, the desired flow rate was 200 cubic meters per hour from 342. So we do that now with only speed control. So we reduce the speed by 42%. But if you see here, when we reduce the speed, the new curve, and if you remember, we had a system curve as well. So the new curve will be this black one. Okay, so, and now the speed is at 200%, and the head will be around 4.8. So, the blue one is the blue one is the new curve for that speed. So this is 200 cubic meter per hour. The new head is going to be 4.8 meters. And here the required power will be, of course, a lot less. And that will translate into an efficiency of 76.7. So there was a decrease of only 0.2% efficiency here. So this is a significant cost saving here, right? If you see this in numbers, with the throttling we use, so the efficiency again reduced by almost 10%. Here it's only 0.2%. Now, so again, these are the pump curves at different speeds. So what happens when we monitor these curves? Okay, so we keep track of the operation point of the pump. If it's running within this best efficiency point, everything is smooth and we don't have any problems. And then when you start having issues and you throttling it, so you are again risking a damage mechanically. And there are of course several ranges that the pump can run, and this is of course designed by the manufacturer. So if you are going from a preferred operation range to allowed operation range, and then you exceed that threshold, then you are in, creating discharge recirculation or cavitation, and over time, of course, noisy operation, high vibration, and then you will risk damaging again, sealing or bearing. And if you are close to the very left on the curve, of course, the temperatures will increase. So, and here is the operation range that we are using in our software. So we will keep track of whether the curve is actually operating outside of the preferred operation range. So the preferred operation range is again the suggested operation range provided by the manufacturer. So what happens if you move to the left or right? You can see that the optimal efficiency will not be achieved, reduced. Of course, if you are operating here, you will have these. If not, you will have the negative effects. So you will, risk reducing or increasing the wear and tear, and you will have cavitation and unstable performance of the pump. So one last example I am going to give here is the cost analysis. So we mentioned that, of course, if you use speed control with a VFD, you can have significant energy savings. So how does that translate into actual money? So we will show that here. So let's start with one example again. So here we have a flow rate of 635 cubic meter per hour. The head is 80 meters. So the energy consumption at that operation point is 253 kilowatt per hour. So the efficiency is 80%. So and now we decrease the flow rate by using a valve and then doing a throttling here. So let's see if we reduce the flow rate from 635 to 360 cubic meter per hour. The energy consumption will also reduce from 252 to 179 kilowatt hour per hour. So, but the head will remain the same here, and the efficiency of the pump will reduce from 80% to 63. So there's a 17% loss there. And of course, remember that we haven't changed the speed. So, and when we turn these into useful numbers, you can see if we were to do speed control instead of throttling, you would have reduced the efficiency from 80% to 70%, 75. So there's a 12% again difference between that, which is equal to 37 kilowatt per hour. So, and if you make a calculation, this would actually turn into $51,000 per year. So that's a lot of energy saving there. And of course, having the real-time information constantly, you can adjust the speed of the pump, in real time. So you can increase again the savings through doing the pump performance monitoring. So overall, what do we offer here? So other than mechanical, electrical, and process monitoring, which we've been doing for almost 20 years now, we are through again adding this pump performance monitoring. We will help optimizing the pump performance, speeds, and of course, which will have additional benefits of energy savings. Then you can decide whether you would want to do speed control or throttling and what would be the effects of that. And of course, more importantly, you will extend the lifetime of the pump and you will have more of a preventative approach. So for instance, if the pump performance curve shows you that the pump is running at a cavitation point and maybe it hasn't damaged the impeller yet, but you will see that. So if you prevent that, it won't turn into damage pits on the impeller yet. So this will be before we see anything on the spectrum that it has actually turned into a cavitation problem yet. So, and of course, automated fault diagnosis and online, again, monitoring will help you identify the root cause of the issue so your pump can run inefficiently due to a simple misalignment only in the pump. So all those issues will also be, of course, was seen through the comprehensive fault diagnosis that the system is capable of doing. And here, one last time, we're looking at this curve. You can see this is the preferred operation range, and we are constantly calculating the curve, the QH curve here, and dependent of the speed, we will create the system curve. So, and then you can see how pump is performing with reference to its system curve. And here you can keep track of the flow, power, and power consumption, and the efficiency. But more importantly, without doing any of that, the system will provide you the automatic fault diagnosis similar to our mechanical fault diagnosis. So you will see if there's a warning or not, if there's something you have to pay attention to. And through only voltage and current acquisition, the system will estimate the flow and head. So this is another important thing to mention. So if you don't have any flow meter or head data, the system will calculate it. If you have it, you can provide that to the software. And of course, total energy consumption will be calculated and monitored. But more importantly, the associated energy efficiency losses or savings will be shown here on an annual basis, so that you can keep track of the energy waste or energy savings here. And of course, using that, combining that with the Artesis automatic fault diagnosis for other problems on the system, right? The pump is working together with pump or motor, and you have shaft, you can have misalignments, you can have seal problems, you can have bearing issues, or you can have rotors. So all that, of course, will be part of a comprehensive predictive maintenance or condition monitoring approach. So this merge with that will give you a greater insight and greater accuracy in keeping track of, again, pump performance, whether it's related to flow efficiency or it's a mechanical, or it might simply be an incoming power issue on the electric motor. So all that will be monitored through one single hardware and software solution. I think that's the most, of course, important part of this approach. And here you can see when an issue on pump performance actually, is prevalent for a long time, that will also show up as cavitation on the spectrum analysis. And here are some examples that we have seen and detected through the system, and a verification using by vibration analysis, which you don't actually need it, but if you want to verify it, you can do that here. So, and if there's, pump seal issues or flow turbulence or cavitations, this, when it's advanced enough, so you will actually see it on the automatic fault diagnosis as well as on spectrum. So this is the end of our webinar, but before closing it and getting some questions, just I would like to summarize once again. You can, only using voltage and current analysis, you can actually have a comprehensive one hardware and software solution to have diagnosis of electrical, mechanical issues together with process changes. And now adding the pump performance curve will give you greater insights for pumps, and you can optimize again your pump operations and then prevent potential issues before they become bigger pumps. So now we can get some questions, and then I will try to answer them one by one. Okay, so let me see. Yeah, if you have some questions, you can write in the chat box and I'll try to. Okay, the question from Gary. In case you don't have the pump curve from manufacturer, how will you arrive at PAP and curves? So if you don't have the pump curve from manufacturer, we won't be able to do it. It's as simple as that. If we have the pump number, we can, of course, during the commissioning of EMCM, we can do that. But yes, we need the pump curve, that's for sure. How does the automatic diagnostic report generate normal caution and high alert zone? It's based on any standards. So this is a question from Gary again. So the cavitation, through the pump performance, yes, we are following again the system curve, and then there are certain percentage deviations from the pump, the best efficiency point, which will then be used as a reference point to detect cavitation points. But if you are asking the question for spectrum analysis, there the spectrum analysis follow the standard deviations from the baselines. But there is a machine learning there. Of course, you start off with a learned model, and then you see how much it deviates. So those are the standards we're following. Question from Samir: do you bring any vibration data? We don't bring any vibration data, but if you want to use it separately, you can use that. I've shown one example in a cavitation case where we have found the issue and the user used separately a vibration analysis to verify the findings, but we don't need any vibration or any other sensor data into the software to make an analysis. So question from Aloson: can this PDM tool detect rotor bar broken issue? Yes, we can detect rotor issues. And that's, of course, has been the case for 20 plus years, but this was not the focus of this webinar, but yes. Is there any AI in back end of this tool? Yes, this is a machine learning. So AI is it's a term that is used very loosely nowadays. We don't want to use the AI, but we use machine learning, because essentially when the system first installed, it actually creates a digital twin of the whole system, and then it detects the existing faults. Then afterwards, it keeps monitoring the deviations from that learned model. So that's actually a machine learning, and that process takes 7 to 10 days. So I must also emphasize that. How to separate normal and caution signals in spectral density. This is a question for another time, but we have done a lot of webinars on this, so it's a very lengthy explanation, so I don't want to get into that. Vibration analysis include RMS only or orbital analysis? We're not doing orbital analysis. We're not using RMS. We're actually taking the raw waveforms sampled at 10 kilohertz, so that's what we're using. In addition to pump curve, so there's another question. In addition to pump curve, what other parameters are needed? It would help if we have the motor efficiency curve too, but other than that, we don't need anything else. Another question. Mechanical vibration tools can detect from low speed frequencies to high frequency and detect more than 50 symptoms, and can Artesis do covering all same vibration tools? So as I mentioned, we do low frequency analysis, high resolution, and high frequency. We can see any problems up to 5 kilohertz. So, and that's probably similar to vibration analysis. In some cases, you can go higher frequencies in high-end vibration frequency tools. But the purpose of the system is, again, not needing any vibration tools, and have enough resolution and enough PSD length or max, so you can see most of the issues that you can see with vibration, but more can be done here by adding electrical power monitoring pump performance curve. How is the pump curve entered in the EMCM? Question from Luke. So we are going to get the pump data sheet, and then the software will do some image recognition and create the pump curve by using that and do an interpolation there. Okay, so a lot of other questions. How does the pump speed affect the flow rates? We already covered that. So if the customer said that this type of analysis is done in their DSS system, what should be our response? I'm not sure if I understand the question, but if they're doing it already, they can add the condition monitoring capabilities into the CS by using OPC. So it would be an addition for that. Can you test the output of a medium voltage drive? Question from Todd. So we have a motor test tool, if you will. There's AMT Pro, but of course, today we're discussing the MCM. But the answer to your question, if the medium voltage motor has a medium voltage transformer, a PT, and a CT, yes, we can do a test easily by tapping into the secondary side of the transformers there. All right, so question from Gary. How will you differentiate between cavitation and load change when in both cases there is a possibility of increasing current spectrum? Now, this is a great question. All right, so I mentioned that we are doing machine learning within 7 to 10 days. Okay, so during that 7 to 10 day learning period, the system will learn each operation point of the rotating asset. This doesn't have to be a pump. It can be anything. And it will learn and it will create clusters, basically a digital twin for every operation point of the system. So this can be different loads, different speeds, and different frequency inputs to the system. So when it's monitoring the system, it will compare that load condition and that spectrum with the proper cluster. This is how it will differentiate and account for load changes in the system. Okay. Another question says, do you have European dealers? Yes, we have a dealer in every country in Europe or in the globe for that matter. Question from Alberto. Service team to install, manage. Yes, the dealers and the distributors are capable of doing everything. Can we get a record of the webinar? Yes, we will. You can actually log into the website afterwards and then download the recording. Okay, good question from Jonathan David. In order to obtain the actual flow, do you measure it or do you estimate it? We do both. If the user has some flow meter and they provide the data through Modbus to our software, yes, then we won't have to estimate it. If not, then we will estimate it. And the error in estimating that is right now approximately somewhere between 1% to 3% error range. That's a good question. Question from Philip. What does MCM mean? MCM is just a name of our previous generation of product, which stands for motor condition monitoring. Will it be able to find which impeller is faulty when in its multi-stage centrifugal pump? Yes, if you know the speed of individual impellers there. So, because each, dependent of the impeller size and impeller number of blades or vanes on the impeller, you will have a certain frequency signature. So we can do that and we can achieve. But this will require a manual spectrum analysis. It's not going to be automatically analyzed, but the system will generate a transmission or driven equipment. In this case, it's going to be pump. So you will have to follow up with spectrum analysis to calculate the impeller or vane pass frequency for that impeller on a multi-stage pump. So it's a more advanced analysis, but it can be done. Does the system also work on a dynamic system, fast changing flow rates? Yes, this depends how fast the changes are happening. If it's within a matter of, let's say, a couple of seconds, no problem. But if it's quicker than that, it might have a hard time to keep track of real-time changes there. So there is a question from, do you consider the station performance? I mean, there are two pumps working in parallel. If you have two EMCMs monitoring those separately, yes, you can actually consider and make some comments about the station performance as well. Okay. I think this is all we have so far. So great questions from everybody, and we are almost at the end of 1 hour period we have allocated for this webinar. But thanks everyone for again joining in. If you have any questions or follow-up questions, you can email us. You can see the email address on the screen, and we will get back to you one by one with your questions. And again, thank you very much, and we'll see you on the next webinar.